Have you ever wondered how two digital devices talking to each other at millions of bits per second actually manage to stay perfectly in sync? I mean, how does the receiver know exactly when it's supposed to listen for each bit? Well, today we're going to unlock the secret behind one of the most clever techniques in digital communications, Manchester coding. And it all starts with a pretty fundamental challenge, the problem of synchronization.
So first things first, let's really get a handle on this challenge. In the world of electronics, timing isn't just important, it's everything. You can think of it like a drummer and a guitarist trying to play a song together. If their timing is off by just a little bit, you don't get music, right? You get noise. It's exactly the same for digital devices. Keeping a sender and a receiver marching to the beat of the exact same drum is a huge, huge problem.
And this really is the core question. What happens when one device is just sending a long, boring, repetitive stream of data? How in the world does the receiver stay locked on, second after second, without its internal clock drifting even a tiny bit out of time? So let's imagine we're using a really simple code where, say, low voltage is a 0 and high voltage is a 1. Now, if you send a long string of zeros, the signal just stays low. It's a flat line. And for the receiver, this silence is, well, it's confusing. Its internal clock, no matter how precise it is eventually going to drift just a little. And a tiny drift is all it takes to start completely misreading the data. And that's really the heart of the issue. Without those signal changes, the receiver just loses its place. It's kind of like trying to read a sentence with no spaces. Sooner or later, it gets out of sync, and the message just turns into gibberish. This loss of synchronization is the exact problem that Manchester coding was brilliantly designed to solve.
So how do we fix this? Well, the solution is beautifully elegant. And I want you to think of it less like an engineering problem and more like a dance.
Officially, Manchester code is what's called a line code, and it combines the data and the clock signal into one. And that right there is the key. It creates a self-synchronizing data stream. The clock is literally baked right into the message itself. So here's the secret sauce. Every single bit, and I mean every one, whether it's a 1 or a 0, is guaranteed to have a transition, a change in voltage right smack in the middle of its time slot. This completely gets rid of that silent or flat signal problem. There's always a beat. Let's go back to our dancers for a second. The sender and the receiver are partners, and they have to stay perfectly in time. Now, in this dance, there's a rule. No matter what, every single beat must have a move. Standing still? Not allowed. That mandatory move, well, that's our clock signal.
And the dance moves themselves are incredibly simple. There are only 2 of them. If the signal moves up in the middle of the beat, we call that a rising edge. That means a 1. If the signal moves down, a falling edge, that's a 0. That's it. Every single bit has one of these 2 moves, so the receiver always knows where the middle of the bit is, letting it resynchronize over and over and over again.
Okay, so let's take this cool dance analogy and look at the official technical rules. Because while the core idea is simple, the way it's implemented has a couple of different flavors.
Now, believe it or not, there are actually 2 ways this dance can be defined. The original version, by a guy named G.E. Thomas, says a falling edge is a 1. But the version we're going to focus on is the IEEE 802.3 standard, which is the one used in classic 10 megabit per second Ethernet. And it's the exact opposite. A rising edge is a 1, and a falling edge is a 0.
And this is where it all clicks into place. Look here. The blue line, that's our clock. It's the steady, predictable beat. The red line, that's the actual data we want to send. And the green line, that's the final Manchester signal. That's our dance. See how for every 1 in the data, there's a rising edge in the middle of our final signal? And for every 0, there's a falling edge? This just perfectly shows how the data dictates the move while the clock provides the rhythm. All right, theory's great, but let's see how this actually works with a real-world example. It's time to put on our dancing shoes and encode a binary string ourselves. So here's our data string, 1, 0, 1, 1, 0. We're going to map this out using those IEEE 802.3 rules we just talked about. Just remember the 2 moves, rising edge for a 1, falling edge for a 0. Let's see what that looks like. Okay, here we go. For our first bit, a 1, we make a rising edge right in the middle of the bit period. Simple. For the second bit, a 0, we make a falling edge. The third and fourth bits are both 1s, so that's 2 rising edges in a row. And the final bit is a 0, so we finish with a falling edge.
Now you might notice there are transitions at the start of some bits too. That's just to get the voltage to the right starting point for the next dance move. The most important thing, the thing to always look for, is that transition in the middle of each bit.
Now, this all sounds amazing, right? It's a robust, self-correcting system. But, as with pretty much everything in engineering, this benefit comes with a trade-off. There is a price to pay for this beautiful synchronization.
So let's quickly recap the two huge advantages here. First, it's self-clocking, which we've been talking all about. The receiver can perfectly figure out the sender's clock. Second, it's what we call DC-free. Because the signal is always zipping up and down, its average voltage is 0. Now, this is actually super important because it lets the signal pass through things like transformers, which can electrically isolate the two devices. Think of it as a safety barrier that blocks electrical noise and stops dangerous voltages from crossing over, which makes the whole connection way safer and more reliable. But here's the catch. Look at this comparison. On the left, you've got a simple code called NRZ, non-return to zero. On the right is Manchester for the exact same data. The Manchester waveform is changing state way more often. See, to guarantee that transition for every single bit, you have to wiggle the signal up and down a lot faster. And this brings us to a really important difference: bitrate versus baud rate. Bitrate is what we really care about: how much useful data gets through per second. Baud rate is how fast the signal is physically changing. With Manchester code, to send just one bit of data, you might need up to 2 signal changes. So the baud rate is always double the bit rate. And there it is. That's the price tag. Manchester coding needs twice the bandwidth you need, a faster, more expensive communication channel to send the same amount of information compared to a simpler code. You're basically trading bandwidth for rock-solid reliability. So let's do a quick-fire recap of the most critical points. 1. Manchester code embeds the clock signal right into the data stream itself. 2. The whole secret is that a voltage transition is guaranteed to happen in the middle of every single bit. 3. Its biggest win is incredibly robust, self-synchronizing communication. And 4. The biggest cost is that it requires double the bandwidth. Simple as that. This idea of trading efficiency for robustness is a central theme in all of engineering. So I'll leave you with this question. Knowing that you're paying a 2 times bandwidth penalty for perfect rhythm, where else in our digital world, from deep space probes to medical implants, might this elegant little dance be worth the price?